Good afternoon, everyone, and thank you for your nice introduction. Before I get started, I just want to thank Alan and Suzanne for giving me this opportunity. And without spending too much of time, I would like to spend some time of my talk in explaining or describing the platform which we have built at IIT Madras, which allows us to work on the postmortem human brain. And very happy to say that we are just a 3-year-old center, and currently we are studying the postmortem human brain at cellular level, all the way from early second trimester up to 91-year-old. We are looking for 100-year-old specimens, and in last 3 years, we have built a platform where we can do the whole brain histology, digitize, and then put it back in 3D. So just to give a little introduction, which this crowd might not need, is it's really important what's the importance of studying the human brain. So the human brain has its unique genetic makeup, and as we are all aware, in the last 20 years, a lot of focus has been on the mouse model organoids, and yes, we can do a lot of interventions. They are extremely valuable, but if we really want to answer and address human diseases, that we definitely agree, everybody sitting in this crowd, that cannot be addressed adequately by studying the animal models. So one of the biggest challenge in working with the human brain is, especially the postmortem human brain, is access to high-quality postmortem specimens. Getting the consent, both for fetal brains as well as for the adult brain, is not trivial. The postmortem interval is super critical, given that what our goal was to really have a very high-resolution histology. And also, many times the argument is you want to go for fresh brain versus a fixed brain tissue. And again, in the last 20, 30 years, the focus has been more towards acquiring fresh specimen to do the molecular work. Then comes the size and volume. And everybody sitting here in this crowd, and given that the workshop was all about the computational platform to put these histological data sets together, one of the challenges has been working with the adult human brain is the number of slabs and slices which you do. The more you do, the tougher the task for my colleague Kirti and the rest of the people who work in the computational side. So one thing we wanted to achieve is how do you process the whole human brain as a single piece, or the adult one with minimal slices, and I'll talk a little bit more about it. To do so, again, the other challenges are what type of stain you would do, how do you go with serial section. Managing all of this digital data is, again, an important challenging task, specifically when we are talking of the human brain. What you see in this particular image is the platform which we have built at IIT Madras, and I will go a little bit more into detail, but I would just like you to focus on the bottom panel, which shows that the several technology and the equipments which was built in-house, which allowed us to really process the whole human brain at such high throughput. Sorry. Cannot move. Okay. So just to bring this to everyone's attention, this was published by Francis Crick in 1993. And the title of the paper was Backwardness of the Neuroanatomy. Once again, a lot of people would be quite familiar with, where they highlighted to really interpret the activity of living human being, their neuroanatomy must be known in detail, and new techniques and technologies need to be developed to really study the human brain. This was 1993. Not that IIT Madras was planning for 30 years to get into this, but this was one of the big motivation. What is the missing piece? And our head, Mohan, is not here. He couldn't attend this meeting, but he always says this, that in India, we realized we are starting very late. If you're starting very late, you want to start straight onto human brain rather than going mouse and monkey, and again, nothing against mouse and monkey brain. So that was the risk we as a center wanted to take, and we thought, okay, if it works, excellent. If it doesn't work, we will see what would be our next step. So as all of you would appreciate, imaging the whole human brain at cellular level is a massive task, and doing this at scale with high fidelity is what we have been able to achieve in the last 3 years. Moving forward, I just want to spend some time. So this particular platform, which I will speak today, what has resulted in the Dharani Fetal Brain Atlas, starts with the postmortem MRI, in-skull MRI. Once again, we are dealing with fetal brain, which is soft, fragile. We do this postmortem MRI after the fetus has been immersed in the fixative 4% paraformaldehyde, but we have a timeline that the MRI needs to be obtained within 48 hours. Once the MRI is obtained, the specimen is extracted after 2 weeks. We then obtain, sorry, this pointer is, okay. We do the surface scan of every single specimen, print a 3D metal mold. In the meantime, we do the graded cryoprotection, and we use this custom-designed 3D printed mold to freeze the entire brain, fetal brain, and we have been able to do this all the way up to 40 gestational week as a whole single specimen using the same dry ice and isopentane bath, but we have optimized it in such a way that with the rate of freezing that we don't end up seeing freezy artifact. We have done this across 100 specimens. So that is something that was our first step or first challenge to be able to do so. We then do the cryosectioning. Currently, our platform allows us to do the sectioning anywhere from 10 micron thickness all the way up to 40 micron thickness using the tape transfer technique. Those are, again, custom designed based on the amount of glue, which allows you to lift each and every section with minimal distortion. Before we take every single section, we do block face imaging. Using UV light as well as white light, and that becomes a second reference after the first reference, which is the in-skull MRI. We use UV curing light to uncure the tape, and we then end up with serial sections, which ranges anywhere for a fetal brain from 2,500 serial sections to an adult brain with 10,000 serial sections. In our center, we conventionally do 3 series of these serial sections, which includes Nissl, HNE, and IHC, depending on what you want to study, and the myelin stain, which again is, in terms of fetal brain, we are only looking at after 27 gestational week. To do so at such a large scale and high throughput, we built the auto stainer, which can now process 6-inch by 8-inch slides, because we are talking the whole brain all the way up to the brain stem. We also built the cover slipper, which you see there in the bottom panel. And we have then worked with, again, most of you would be familiar with the Huron digital scanners, which is now we are able to digitize at 0.5 micron per pixel in plane resolution, close to around 20 to 30 minutes for any 6-inch by 8-inch slides. We then have a strict QC process after digitization. Once the QC is cleared, it then comes to our viewer, where you can then access across all the modalities of the entire brain, including the MRI, block face imaging, and the serial histological sections. The data which I will show you today is from the Dharani Atlas, where we used 5 fetal brain covering the entire second trimester, and we built our own atlas annotation tool, including the ontology, because many times the nomenclature or regions are defined using the adult brain structures, which is still developing, and that's the work in progress. We then use the stack alignment, put all of these data across different modalities, and then register it to the MRI space. And I have got my colleague Kirti here, who will be happy to discuss any of this in detail in the next 2 days. So this is the work which came out early this year. To the best of our knowledge, this is currently the largest data resource, digital data sets of the developing human brain. We released 5 brain data sets with a very high sampling rate because each of these specimens came from 14 gestational weeks with close to 1,400 sections all the way up to 2,500 sections. Of course, as all of you would know, annotating these many brain regions was not an easy task, and my sincere acknowledgement to the entire team, including the clinical partners who made this really happen. What this real atlas content is, you can access the NISL datasets, the H&E datasets, MRI, block face imaging, as well as the annotated data from 14 to 24 gestational week. All these 4 specimens were sectioned in a sagittal plane. And most people are used to of the coronal brain sections, but I have to say when we started this, we wanted the alignment because you want to put it back in 3D, so we control the X and Y plane more, but since then, and we have 1 specimen in the coronal, which is for 22 gestational week, but since then we have evolved, and now we are able to do in all possible transverse as well as the coronal plane. This data was made open source. You can access all of those 5,000 data sets which we have made it here. You can access across the modality, the atlas annotation, the 3D reconstructions, etc. using this portal. And just a short video to show what the interface looks like. And I would be very happy to take any questions or see if you have anything. So is there a way if I could do this? Move the video a little forward. Okay, if you could go just to the middle, around 1 minute mark. Thank you. Yes, so this is a 22 gestational week data set. What you see in the main screen is the atlas annotated one. You can click your region of interest. You can access the ontology. Following that, on the bottom panel, you get access to the block face imaging, the serial sections, as well as the reconstructed image. But for every brain, you also have access to the MRI data sets. And this is so in terms of how it compares with the current, previously available atlases, in the fetal brain, the 2 main atlases are the Bayer and Altman, which covers across the entire gestation from 1st, 2nd, 3rd trimester, as well as with Allen Brain Institute, which released in 2021 3 fetal brain data sets. What we have here is more in terms of the sampling, the number of sections which have been annotated, as well as across different modalities from MRI, BFI, histology, and we marked and identified close to 500 plus regions across the entire 2nd trimester. This is just to give you an example here of a 17 gestational week from the same Dharni atlas, which has been put it back into 3D using the NVDI viewer. And once again, Kirti is here to answer if you have any more detailed question. But as you would see, you can now access this in 3D as well as the cellular level data sets. So what came out of Dharni, apart from this being a large data repository, was we were able to characterize the developing cortex in the entire human brain from the occipital, frontal, parietal, and orbital cortex across 14 to 25 gestational week. We were then able to appreciate the difference between the developing cortices as well as the cells. And now we are using these data sets to do the cell count region-wise, as well as do several immunohistochemistry markers to show the developmental trajectory across the entire cortex. We also reported the development of earlier bed cells just at the border where you would future motor cortex is a pit. This has not been reported well in the developing human brain. Along with that, we were able to show the rotation and development of lateral geniculate nucleus in the human from the 14 gestational week all the way 24 gestational week, where you also start seeing the layering. Along with this, there were several other findings, including in the brainstem, but I'm just giving a little snapshot where we reported several nuclei within the developing amygdala, which has been identified in marmoset monkey, but not in the fetal human brain. Same with the lateral developing of the interpennicular tract, where we were able to trace all the way up to the red nucleus and how it surrounds by the time you reach 24 gestational week, as this is one of the first fiber tract which develops in the developing human brain. This is a short summary of our platform, where once we have these digitized histological data sets, we are able to do the stack alignment. Each of these 2D digital data sets, we then work on cell detection, classification, laminar organization. We are now building, because now we have gathered close to 50 plus specimens in the developing human brain, we are building the morphometric platform. And we want to build a platform where you can query, looking at these entire data set, registered to one reference point, and you can look at the developmental trajectory of any region of interest and make that as an open source. Okay, I'm getting a signal, time is up. So now, because we were able to do this over a large sample data sets, we are now building tools which will not be at the same resolution, but you can now annotate and make this atlas annotation more as an automated things. And you can then look at each region separately, look at it in 3D as well as in 2D. So in short, the platform what we have built is bridging the gap from cell to volume. Without going too much into detail, because I've got the signal, this is a big picture, and I'm happy to connect with everyone here for the next 2 to 3 days. And in summary, we have this platform which now not just has done the fetal brain, we are looking at, or we have processed adult human brain, which are equivalent to a few petabytes of data sets with 10,000 plus sections. We are looking at disease brain, neurodegeneration, ischemia, and also developmental disorders, which we have published recently. So in short, we need comparative data sets across from animal models, organoids, and human, if we really want to understand from molecules to behavior. My sincere acknowledgement to all my collaborators. It's increasing every day, and we are very happy to connect with many people over here and put several more names on this map. And today I'm the one presenting this work. We started with 5 people 3 years ago, and it's a team of more than 120 plus at the center. And my sincere acknowledgement also to all our funding bodies, sorry. It's just, okay, I think time up. Thank you. Do we have questions now or later?
I think maybe for one question, just one question, if it's an urgent one, otherwise later.
I haven't got in place yet the nonlinear warping from early time points to late time points, so you can build a 4-dimensional.
Yes.
You've got that in place yet?
We have not got completely in place, but that is what we are building, because we annotated region-wise, we have the volumes, we have the measurement, we have volumes across MRI versus histology, and we are building tools to do automated cell detection. So one could put a query, for example, LGN, how much does it increase in volume across the age? What's the cell number? And when you do specific markers, how these cells are getting differentiated from this to this age group. Voxel-wise, that's what we want to do. Yes, yes. Okay, so I guess that was one question, but happy to take more in the next 2 days. Thank you.